Hi class, in this short video I'm going to discuss the solutions to the thermodynamics or thermochemistry worksheet that I had uploaded. So first things first, the first question essentially discusses, it requires you to tell how much work is done in joules, the work done in joules to inflate a balloon from 0.100 liters to 1.85 liters. So you can envision that there is a balloon which is deflated, so its volume is like 0.100 liters, and now we are going to put in air into that, so it becomes a 1.85 liters. That means work is being done by the system here because there is work that is involved by the gas molecules internal inside the balloon to push against the air. So the work that you do here, the W, will be a negative work, and you will calculate that by P times delta V, because this is an expansive process. So recall from lecture notes that expansion always is negative, compression always is positive. So negative P delta V is the amount of work that will be done. The pressure is given to be 1 atmosphere. Delta V is 1.85 minus 0.1.85 minus 0.1, which is negative 1 times 1.75. So your answer will come out to be negative 1.75 liter atmosphere. So now you have to use the conversion factor, since 1 liter atmosphere is equal to 101.3 joules. You have to convert the 1.75 liter atmosphere by setting it up in such a manner that 101.3 joules, the liter ATM and liter atmosphere cancels out, and what remains, that's what you need to work on the math of. And when you multiply them, and I'm doing that on my calculator right now, it's going to come out to be negative 177 joules. So that should be your final answer. So always remember, expansive processes, W is negative P delta V, whereas if it's a compressive process, W, the work done, is going to be a positive number. Okay, let's discuss the next question. The question is, when 1.01 grams of sucrose is C12H22O11. So when 1.01 grams of C12H22O11 undergoes combustion in a calorimeter, the temperature rises from 24.92. So my temperature initially was 24.92 degrees Celsius, and it becomes T2 becomes 28.33 degrees Celsius. So it rises by approximately, you can say, close to about 3.5 degrees or so. The question is that you have to determine the delta E reaction, the heat of the reaction, for this combustion process, and the units should be kilojoules per mole. So there are a couple things that are given. The heat capacity for the calorimeter. The calorimeter is at 4.9 kilojoules per degrees Celsius. Recall that the delta E for the reaction, which is the internal energy, is a combination of heat and work, and this is the one that is at constant volume. So whatever work is done by the reaction, essentially that is going to be picked up by the calorimeter. So you have to think about two different things here. One, that the heat, the net heat, the overall heat associated with the calorimeter will be equal to the heat capacity of the calorimeter times the temperature change. But where is that coming from? That is basically coming from the reaction. So the reaction that you have, that will be negative Qcal. And we'll have to, of course, convert the grams of the sucrose into the moles of sucrose to ultimately predict this answer, find out this answer, determine this answer in kilojoules per mole. So let's take one step at a time. What we are going to do is we are going to calculate first the energy associated, the heat energy associated with the calorimeter. And since heat capacity is given to be 4.9 kilojoules, it's always a good idea to put the units so you know what's getting cancelled out. The difference between T1 and T2, I'm just working that out now, that comes out to be 3.41 degrees Celsius. So the heat capacity times the temperature difference, delta, the degree Celsius cancels off, and you end up with 16.7 kilojoules of energy. Now, where did that heat come from? That heat came from the reaction. And so one can say safely that negative 16.7 must have been the amount of energy that got released. And so now converting the 1.01 grams of sucrose to moles of sucrose. In order to do that, you'll have to divide the given grams by the molecular mass of sucrose that I calculated early on, and I have that number as 342.3 grams per mole. Recall, the way you calculate the molecular mass is simply multiplying a particular kind of atoms with the atomic weight and just adding them all together. So sum of every single atom, the atomic mass that is put together in that formula. And so this should give you 0.00295 moles. And so now simply taking the energy, the Q for the reaction, which is negative 16.7 kilojoules, divided by that value for the mole, which is 0.00295, and when you calculate that, that comes out to be a negative value, negative 5.66 times 10 to the power of 3 kilojoules per mole. That should be your final answer. Okay, so here the third question is an LP tank in a home barbecue contains 13.2 grams of propane. Propane is C3H8. Calculate the heat associated, this has to be done in kilojoules. Calculate the heat associated with the complete combustion of all of the propane in the tank, and then the equation given is that propane C3H8 reacts with 5 moles of oxygen to give you 3 moles of CO2 and 4 of H2O, and for this the delta H associated is negative 2044 kilojoules. So that entire equation, thermochemical equation, will have to be provided to you. So first thing that you should do, since you're given only the amount of propane that is present in that tank, is that you should convert the kilograms of propane into essentially moles of propane. So since 1 kilogram has 1,000 grams and it's C3H8, so the molecular mass of that is 3 times 12 plus 8 times 1, so 44 grams of propane will be 1 mole of propane. So you can say the kilogram and kilogram will cancel, the gram and gram will cancel. You're basically employing 13.2 times 1000 divided by 44, and that will give you the moles of C3H8. And now you can simply just use the equation. From the given equation, we know that negative 2044 kilojoules of energy is released. So you could say that 1 mole of C3H8 is going to release negative 2044 kilojoules. So the total amount of energy that will be released when you work out the math comes out to be 6.12 times 10 to the power of 5th kilojoules. So you can use the thermochemical equation and notice the amount of heat that was involved. Like I said in class, you can treat the amount of heat that is either absorbed or evolved in a reaction. It can be treated as a reactant or a product in a per mole basis, even in a stoichiometric sense.